And obviously I've posed around a few questions about what I want to know about you, so I thought I'd just kind of balance that out a little bit about me and about I chose physics at university, about where it's taken me so far. So I went to Shrewsbury Sixth Form College, which I think there are about 3 or 4 of you in the audience possibly that also, I can see some hands, brilliant, that's an excellent representation. So I went to Shrewsbury Sixth Form College where I did physics, chemistry, a little bit of further maths, economics and maths. That took me to Oxford University where I did physics for 3 years. And then I decided, on a whim, I say on a whim, I decided, quite to my own surprise, to take up a PhD, a second degree in physics with the University of Strathclyde. That was a PhD in plasma physics. And although the University of Strathclyde is in Glasgow, it's actually based in Oxfordshire, in the research laboratory that I work at now, which I'll talk about in a second. But through that time, that PhD time, I took a lot more than just getting a doctorate in physics. I worked with some amazing teams. I'm an experimental scientist. When you work with high-powered lasers, you tend to work in quite large teams. Obviously, they're not as large as the teams you might find working at CERN or any of the really big facilities like that. I also did a lot of traveling, and that's one great thing that you get from science, and especially as an experimental scientist, is that you have to go to the best places in the world to do your science. You also get to talk to people all over the world about the science that you're doing. As a key part of our research is to talk about the research to the community. And so my highlights have been, New York, Japan, and Frankfurt. To me, those are my PhD. They're the ones that really kind of stuck out to me. And the last one, 3 T's, training. It really gave me a unique skill set, which I'm still in research now, but if I wanted to take that skill set somewhere else, I would have been highly employable. It not only gives you the ability to analyze complicated data sets and try and figure out what on earth they're telling you and be creative and think of new science. But there's also skills in communicating difficult concepts to people outside of your expertise, and that's something that can really take forward into many different areas. And then just a little bit of my journey. I am an experimental scientist. That's me in one of the target chambers that we use for laser physics. And that's picture down there is of one of the Gemini lasers, because the lasers that I work with are rather different. The kind of lasers that you will see that you can get handheld, that they become really full systems. And my research, my PhD journey ended in 2012 when I managed to write this awfully big thesis, which was very daunting at the time, and I managed to do that. And then they gave me a PhD, which is excellent, because now that I'm able to use a title that is both gender and marital status anonymous, which is excellent for me. So moving on to my talk title, I want to kind of use the next 50 minutes or so to talk about my research field. I work with the most powerful and the most intense lasers in the world. And I know that's quite a good line to start with when you're talking about physics and experimental physics. But I really want to get a bit of a grasp on what that means. What do we do with those high-powered lasers? What do we do with the physics that we learn from them? That's hopefully you'll get an idea of what that means towards the end of it. And I will be asking you at the end with your vote pads. I'm going to give you 3 examples of the physics that we do, and I'll be asking you to vote on what you would do if you were in my position, you were an experimental research scientist. So lasers, when I say I work powerful lasers, normally the kind of image that people have in their head, these big systems that can do a lot of damage, they're not eye safe, they're not skin safe, and that's true. These kind of lasers pictured up here are considered quite powerful lasers, and they will do a lot of damage. And so that kind of leads me on to this next question. Those are lasers that you can buy off the internet, but do you have a laser at home, for example? And that doesn't just mean the kind of lasers that you can point around the room. That's kind of any old laser. That should give you a bit of a clue. Alright, I'll just cut that off so we can carry on. So resignedly, yes, most of you have a laser at home in some form, whether that be the one that you can play around with. And there's some of you, think that you don't have a laser at home. Well, actually, most houses will, most people's bags phones, most appliances that you have in the home will have some kind of laser equipment inside them, making them run. And whether that be something like, in the case, a DVD drive, a CD drive, back in the days when we used to use these, they were dependent on laser technology existing, and they still are. Blu-rays. The very reason that a Blu-ray works is because it's using blue wavelength technology to read the information on the CD. Blue wavelength is shorter than red or green, therefore it can read smaller etchings of data etched onto a CD. You can get more data on a single CD, and that's why Blu-rays tend to be the ones where you can get your high definition viewing high definition films onto a Blu-ray disc. The lasers are, the really powerful ones. You can use them to actually cut through steel. So lasers, also just being a form of light, they are a tool that can do a lot of damage. A lot of people say, what can you do with lasers? A lot of people will say, laser cosmetics, laser surgery and things like that. That's what most people think the best application of lasers is. But there are quite a few other applications, and that's because the lasers that I work with are not visible. They're certainly not compact at the moment, but they really are quite powerful. Indeed, they are giant lasers. And I really like this analogy, and this still works, in spite there's a ridiculous date on when Austin Powers came out, and I don't want to think how long ago it was. But the idea of these really big laser installations, well, that's really not that far off, actually. This is an aerial shot of the Rutherford Appleton laboratory in the kind of south of Oxfordshire. This is where I work. And anyone who knows RAL, or Rutherford Appleton Lab, might recognise these features. That's a synchrotron up there, it's called the diamond synchrotron. And down here is the ISIS neutron facility. But right in the middle, in these buildings here, are housed two of the most powerful lasers in the world. So we have not one, but two ultra-powerful lasers in this postcode, in this area. And so these kind of swamp the size of our lasers, but they still are quite big installations. They really aren't something that you can just wheel around on a cart at the moment. We're working on that one. But just to give you a kind of a little bit of an inkling on what super powerful means, and high intensity actually means, we're just going to go back to basics. There's quite a few of these back to basics in my talk, so don't fear, there's not too many equations. The first one just is power. And when we think, what is power? What are we talking about when we measure something's power? Well, we're measuring how quickly energy is delivered in time. So just EOT. Now, the kind of energy that we deliver in a single pulse of the lasers that I work with. The lasers that I work with are not continuous wave, like a laser pointer, for example. That's a continuous wave laser, continuously shining. And these are packets of laser light. So we press fire, and you get a packet of photons, a packet of laser light, a single pulse. But contained in that single pulse is about 500 joules. Which is really not that much, actually, because 500 joules will heat a gram of water by 1 degree. So really, actually not that much energy. However, we have managed to engineer that energy into a form of light. We've also managed to engineer it into a pulse that lasts 500 femtoseconds. That's 500 times 10 to the minus 15 seconds, half a trillionth of a second. An incredibly, incredibly short period of time. You do the maths there, and you'll get 10 to the power 15 watts. A petawatt is what we call that. And that's roughly about 10,000 times the power that the UK national grid is pumping out right now. So that's a really extreme power. But all we've done is been a bit clever with how we deliver energy in a certain form and how we compact that energy into a tight amount of time. Now, the wonderful thing about lasers is that despite being able to compact it in time, we can also focus lasers down in space. They're just a form of light, and like any other light, you can focus it down with a decent-sized lens. And the kind of lenses that we work with are really quite substantial, but nonetheless, they are able to compress that laser pulse down to a really small spot. And this is what we mean by intensity. Intensity is just how you measure your energy that's delivered in a certain amount of time and over a certain area. So the area, the focal spot, that laser spot that we can squeeze that light down to, is about 5 millionths of a meter. That's 5 microns. Human hair, your hair, is about 100 microns. So our laser spots are focused down to a 20th the width of a human hair. It's an incredibly small spot. You start doing that and put that into your calculator, and you'll get an incredibly high number. 10 to the power of 21 watts per centimetre squared. That means a lot to me, because I know what these numbers and these funny units mean and what kind of physics that entails. But to most people, that intensity is a bit like taking all of the sunlight that's shining down on the Earth right now. And if you could, with a Earth-sized lens, focus all of that sunlight to the top of a pinhead, that's about the same intensity contained in a single pulse, just one single pulse lasting a half a trillionth of a second. When we press fire, we manage to generate that light intensity. So again, it comes down to just being a bit clever. We're being a bit clever how we've engineered energy into a packet of photons that have been compressed in time and space. Now, I hope after that introduction, you're all starting to think about what would happen when you fire one of these laser pulses at something. I'm an experimental scientist, so that's pretty much the coolest part of my job, is when we get to press fire on the most powerful laser in the world, and you stick a tiny, unsuspecting target in the way. You're looking down into a target chamber right now, and on the top of this kind of pin sits a flag-shaped target, a piece of metal in this case, just an ordinary piece of metal, and it's just sitting there waiting to be obliterated by this super high intensity. And when it does, you get this burst of what we've captured here on the digital camera, we see as light. What you're actually looking at is what we call a laser plasma. So plasmas, I guess that's, if you're a sixth form major, it's not too unfamiliar term, but plasmas most days in people's vocabulary will be used to things like these plasma balls or the plasma in blood, for example. But they're quite different plasmas, and I hope that now you'll kind of realise the difference here. Plasmas in physics talk about a completely new state of matter. So it's just going back to a fundamental model of matter here. I hope Harry doesn't mind, this is a very basic drawing of matter, but we'll just keep to the kind of fundamental level at the moment. It's just thinking about the matter can be in 3 states on Earth. We're all used to those, solids, liquids and gases, so we can all imagine how you get from one to the other. We've all done those experiments since we were like 7 or 8 or something. But there is actually a 4th state, and that's when atoms are completely broken down to their constituent parts. So those negative electrons and those positive nuclei or positive ions are kind of all coexisting, but they're free of each other. The electrons have been completely freed from that central positive nuclei of the atom. This is what we call a plasma state of matter, a charged or ionized gas. The best way to think of it is really the 4th state of matter. But in order to get to that 4th state, you really need quite an extreme condition to formulate that plasma, because they're not really that readily available on Earth. There are a couple of examples. Lightning and the aurora lights, for example, are great examples of plasmas forming naturally on Earth. And they're formed, in the case of lightning, by the extreme case of electricity being drawn through from the clouds to the ground by the potential between them. And as it does so, the electricity, a current of electrons ripping through the air, breaks down the air. It knocks off all that battering of the electrons as they travel through. They knock off some of the electrons in the air, and they cause a plasma state, but only momentarily, because that plasma state will very readily go back to being a gas. And as it does so, it gives off its excess energy in a flash of light. A flash of light that we see as lightning. And a very similar process for how the aurora lights form, except this time the plasma is formed from all those energetic particles that the sun is spitting out and then colliding at the top on the poles of the Earth. So there's natural forms of plasma, but the plasmas that we form in our labs are actually quite something else. And it's just worth taking a back step about where that comes from. It would be too simple to say you shoot a laser and you get a hot plasma, because most of us, we're all physicists here. We all want to think about the physics that's going on. And so we have to think about laser in its fundamental form. We think of it, in this case, as an electromagnetic wave. So when it has an electric component and a magnetic component all kind of happening at the same time. But let's just focus on the electric field of that laser pulse. The electric field in a super intense laser pulse, when the light intensity gets so intense, the electric field itself actually does the ripping apart of the atoms. The action of that electric field is what we call to suppress the Coulomb potential that's acting between that negative electron and the positive ion. So an electron or an atom in the vicinity or in the field of this huge electric field, instead of sitting there and binding itself in a normal atomic state, will actually, that attraction, that Coulomb potential between will be completely suppressed. It will no longer feel the existence of the positive ion around it. Instead, it will be completely dominated by the electric field of the laser pulse. The electric field of the laser pulse is oscillating. So the electron falls apart from the atom and then it begins to oscillate. But we live in the real world, so instead of just the single electron theory or the single electron model, think of that as many electrons. In the focal spot of that laser, many electrons are now vibrating, oscillating at extremely high speeds, high frequencies. And there suddenly becomes an interaction between that laser and the electrons inside that forming plasma. There's not only an interaction, there's also an absorption, exchange of energy. There's energy being absorbed from the laser into that packet of electrons inside your plasma. And that process is one of the fundamentals of laser plasma physics. We're constantly trying to understand that interaction between the laser and the plasma being the free electrons in there. And we also try and work out how we can control it, or what we can do with that plasma to give us more understanding, possibly about the world around us, or even about new technology. So talking about plasmas, I said that they're intense, but just want to give you a little question here about how you think how much energy is absorbed into that plasma. And when energy is absorbed into vibrating particles, we call that temperature. So how hot do you reckon these laser plasmas are? Alright, I'll give that a couple more seconds and then I'll collect it in. Right, we've reached our lucky 90, so I'll collect that in. Okay, so that's quite an even split with the last two. So 3% is about 6,000 degrees. That's actually not that hot really, 6,000 degrees. Plasmas at 6,000 degrees are probably most of the plasmas that you found here on Earth. Some plasmas in TVs or plasmas in plasma balls. 6,000 degrees is pretty hot in our macro world, but in the world of plasmas, not that hot. Neither is 30,000 degrees. 30,000 degrees is about as hot as the plasma of lightning. So in that lightning strike, in that bolt, that's about 30,000 degrees Celsius. So 58% of you were correct that actually we can get up to a few millions of degrees Celsius. We can boil, superheat, rip apart those particles into a super hot plasma that will be on the order of a few millions of degrees, maybe give or take a little bit below, and sometimes even higher than that. But when I'm talking about super intense lasers and what they do, their plasmas are not only very energetic and very hot, but there's something else, a feature of them, which is very interesting as well. And that comes down to, start thinking experimentally now, not only are you superheating it, but you're doing it so quickly, so incredibly quickly, half a picosecond, an incredibly short period of time. At temperatures of a few million degrees, those particles will have some kind of velocity associated with them. And if you shoot a solid target, the time it takes for those particles to then start to expand, because hot things expand, start to expand until they decrease in density, you're talking of a few nanoseconds, a few billionths of a second. But you've heated your plasma in half a picosecond, which is 1,000 times faster than a billionth of a second, 1,000 times faster than a nanosecond. So you've actually heated your plasma faster than the particles can actually expand and decrease intensity in density. So you've formed a plasma that is as hot as the centre of the sun in some cases, because that's on the order of millions of degrees Celsius. You've also exerted a pressure onto that target. Now that's a bit counterintuitive sometimes, but that comes down to the fact that lasers, we've talked about them being an EM wave, an electromagnetic wave, but you can also think of lasers as being photon guns. And photons, despite being massless, do have some kind of momentum associated with them. Some of the energy of those photons is absorbed by the solid target, but actually about 50% of the laser light is reflected. It's just completely thrown in the opposite direction. And when you have that change in direction, that change in momentum of the photon coming in and bouncing off the surface, you're going to have some kind of force associated. And a force over an area is a pressure, right? So we've got a pressure associated with that laser pulse slamming into that target. That laser pulse further compresses your target. So you've started with something that was solid density, and now, just by using the laser pulse itself, you can squeeze it down to an even higher density. So we can squeeze material down to a density that's much higher than most solid materials on Earth, much higher than iron in some cases. And that gives you one of the first clues of what you could do with a laser. And that's starting to use your laser plasmas to explore materials that are outside of this Earth. In fact, outside of the solar system, even. Because outside of the solar system and in the outer universe, most of what we see, or the visible or known universe, you should know what I mean now, we've just been talking about dark energy. We're talking about the visible or known universe. Most of it is in the plasma state. So actually we're kind of weird here on Earth that we don't have plasmas everywhere. But everywhere else in space, most of it is made up of plasmas. But those plasmas really have quite extreme conditions associated with them. In the formations of galaxies and the birth of stars and so on, all these weird and wonderful things that happen light years away, it's all happening under a very high temperature and sometimes high density plasma state. In the centre of our sun, or the centre of other planets even, you get this weird state that's a bit like solid, but also it's really hot, so it's kind of like a plasma as well. And that's a whole realm of physics to understand there. And also in extreme phenomena like the remnants of supernova explosions, the death of supermassive stars. All of these crazy galactic events occur under these extremely high density and extremely high temperature plasma states. And just using the first example there of what I mean is of how we can study those in the lab. I'm going to refer to this, and if anyone's keeping up with their scientific news over the last month, you might recognise this picture. This is a supernova that was captured really recently, really good for this talk, on the 23rd of January this year. That's a supernova exploding in our nearest galaxy, I believe, in OH2. And it's pretty bright. I think it might be actually already starting to reach its highest brightness now, so any of you keen astronomers will be able to capture that. But I just wanted to pick up on this last sentence from someone who wrote it up on the internet. It's talking about, they called it a Type 1a supernova, so there's the remnants of a white dwarf, and talking about debris expanding at 20,000 kilometers per second. So that's quite an extreme state there, because that's not just going to be debris and matter. Most of that's going to be in the plasma state, energetic particles flying out into a relatively cold atmosphere very, very quickly. So how might we replicate that in the laboratory? On the left-hand side here, I've got, it's a side view of a puff of gas that has had a laser shot straight through. So you're looking side on. Now because the target, in this case, the thing you're focusing on, is a gas, the laser is actually just able to penetrate all the way through. There's no reflections going on here. As the laser penetrates all the way through, it forms a very hot cylinder, because it's superheating the material into plasma, a hot cylinder of gas, think about it like that. But surrounding that cylinder is a relatively cold gas, puff of gas. So what you're replicating there is hot plasma, very, very hot plasma, expanding very rapidly into a relatively cold atmosphere. And that's one way of modelling what happens in a supernova explosion. If you just focus on the left-hand side first. I'll run this a few times because it's only, it comes quite quickly. And you can see that the cylinder forms quite quickly, and it's relatively smooth. Okay, this is experimental science here, so it's not going to be absolutely perfect. But it's relatively smooth, and then it expands out, and then you get these weird fluctuations. So what you're actually looking at here is a density map. So it's a way of marking how dense the particle populations are. Because on the right-hand side is a model, is a theory associated with supernova explosion. And they've used their plasma theory to try and map what happens when this super hot cylinder of plasma is expanding. And as you can see, the comparison is not that bad. Oops, I've got this cursor off. It starts off smooth, and you get these kind of weird, the fingers growing. You can see them on here, but the fingers that you saw a second ago, you can see growing. What those fingers were actually in plasma physics is what we call plasma instabilities. So that's where that hot plasma expanding really rapidly into something cold. So it triggers an interaction with the particles that means that all of a sudden, instead of being beautifully smooth and writhing outwards, you get these fingers. And when they say instabilities, it's a bit like what Harry said about the kind of dark energy. Instability is a bit like saying it's hard to predict. It goes unstable, it goes really hard. It doesn't follow a beautiful equation that goes on in time. It suddenly becomes a bit manic and chaotic. And instead of smooth, the fingers get worse, the imperfections get worse, and they grow. And modelling that is extremely hard. How do you model something that's pretty much chaotic or unstable? That's a really hard thing to do in physics, but that's a lot of plasma physics is surrounding that. And moving on to kind of a stellar or planetary core science. The kind of realm of physics that we're talking about here is something called warm, dense matter. That warm, dense matter is what I was going on about when I was talking about matter being in both a solid state and also the plasma state. It's a really extreme state of matter in which the equations of state of physics that apply here on Earth don't normally apply to warm, dense matter because they're so extreme. There's some weird things to do with volumes and pressures and temperatures going on. And as physicists, we'd like to be able to map those and explain those extreme conditions. And looking at things like the opacity of the sun. So that's trying to explain why a photon produced at the centre of the sun takes millions of years to travel all the way through the hot, dense plasma that is our sun and out into space, and then finally 8 minutes towards us. So that's a photon having to work its way through dense, hot medium, and that's called looking at the opacity of the sun. But these are really quite extreme states in our universe, and extreme states that we just simply would not be able to go very close to experimentally. The best that we can do is to replicate those conditions in the laboratory and then test them and compare them to our theories and our current understanding. And when they match up, or when they possibly don't match up, well, that's a bit of physics. That's some new knowledge that contribute to the world there, and that's the process of physics. But you need super intense lasers to generate these conditions. That's the key point here, that lasers are very good at producing these extreme states. And these extreme states are quite beautiful, actually. This is just a bunch of pictures that we've captured in experiments on just a digital camera. Looking down into the target chamber again, you can just about make out on this screen, is just enough high resolution. Tiny little flag target right there that we then blow up with a super fat laser. But it's actually looking at what's coming out of there. That's the really interesting part there. Because what you're seeing there is light. You're seeing light that's been reflected and scattered off some of the energetic debris and particles that are spraying off that target. There's actually a lot more than just light flying out in that spray, and that's the invisible stuff that we can't see. We can't see on the digital camera, but that's actually the really cool bit. It's normally the really most exciting bit, the bit that you can't see. Because in that beam of stuff, that beam of radiation, we've got high energy electrons. We've also got X-rays, so high energy photons. Even higher energy, we've got gamma rays flying out, and we've got some protons, so we've got positive particles, and even heavier positive particles, so ions flying out at the same time as well. And what's really interesting about all of these species of radiation is they're flying out at or near to the speed of light. So they're really, really high energy bursts of radiation. And they've got some really great qualities associated with them too. One being that they're bright. So there's a lot of them. There's a lot of that radiation given off in a short period of time, a very fast duration, as short as that laser pulse. And it's really directional. And that's the key bit that makes it really interesting in terms of technology, which I'm going to go on to now, is how you could use that radiation for something other than just making pretty pictures on detectors. And one of the reasons why it would be useful for technology is that the conventional way of accelerating particles or producing energetic beams of radiation is using something called radio frequency cavities that kind of looks a bit like this. There are variations of them, but they're solid structures. They're at approximately on the scale of meters. And you put them back to back if you want to go to higher and higher energies. And that's why big structures that you see like on the diamond map I showed you earlier, and also underground in parts of CERN, you've got meters and meters of these radio frequency cavities that are pushing and pulling charged particles so that you speed them up from rest to a really, really high energy. And if you're really good, you can get them up to like almost the speed of light to do really cool experiments with. Now the accelerators that I'm talking about in my plasmas are a lot smaller. So they're on what we call the hundreds of microns scale. Now what does that mean? What does that actually mean for technology? I've said that we can create bursts of energetic particles that emerge from a bubble of plasma that could be hundreds of microns in diameter. Now, instantly you might think, well, that's your compacting particle accelerators, or miniaturizing accelerators and miniaturizing radiation production. And that is when you start to compare the size of other systems, conventional technology, in a way what we're doing. Because all of these structures, despite diamond being a synchrotron source, a source of X-rays, is actually powered, the X-rays are formed by having an electron particle accelerator going round and round. And ISIS there starts off as a proton accelerator. Whereas right in the middle, we've got our little lasers. Now there, we've got bursts of high energy electrons, protons, ions, X-rays and gamma rays, all coming out from the same laser system from a bubble of plasma that's 100 microns in size. Now, any of you who's switched on to what I was saying earlier about these laser installations, the lasers themselves are quite large. So I'm certainly not talking about a particle accelerator that would fit in the palm of your hand, but I am talking about something that could be quite flexible and in time, when as lasers shrink down in size, could be considered quite small and compact itself. And where that would be useful is in the application of accelerators that perhaps are a bit away from looking at fundamental physics and other areas of science. One application that would really benefit from a flexible, almost compact, certainly tunable source of high energy radiation is in cancer treatment, which some of you might not, unless you read my bio, you might not have guessed that I was going on to this. Yeah, but one of the applications of particle accelerators is in cancer treatment. So this is a picture there's a tumour located where the red spot is, and this is a patient that's been treated by X-rays. So that's traditional cancer therapy, cancer radiotherapy. That's irradiating the body with X-rays and working it so that the X-rays actually destroy the dangerous cancer, so that the body can get rid of those cells and hopefully you'll be treated by that. But there's an alternative to using X-rays, an alternative form of radiation. And instead of irradiating the spine and the brain in this case, this radiation will not only irradiate the healthy, the cancer tissue around here, it will also kind of limit the amount of exposure that healthy tissue has to radiation. This radiation is energetic particles, would you believe? sticking your head in a particle accelerator is quite an interesting concept. But it's something that can be trusted. It's just a different form of radiation. We know as physicists that all that means is that radiation interacts with your body in a slightly different way. And protons, in this case, interact with your body in a way that's beneficial for treating deep-setted tumours beneath the skin. And that all comes down to how this radiation interacts with matter. Again, this is my only picture of a graph, but there had to be one, being a physicist. But this describes very nicely the difference between treating with X-rays and treating with protons. Now this line here is what happens when a relatively energetic X-ray hits your body. So if you think of this outside the body, this is inside the body. And as the X-ray enters, it starts to deposit some energy. So it's energy that it started with, decides to deposit that energy through the body, and it peaks and then starts to drop off as it goes further into the body. Now the proton, a positively charged particle, does something slightly different. So as it enters the body, it deposits some of its energy, so this is about 25% of its energy. But as the particle, as the proton slows down, it slows down because it's crashing into your cells, crashing into parts of your body, it starts to deposit more and more energy locally. And it actually deposits most of its energy where the particle comes to rest. And you can tailor where this peak is simply by changing the starting energy of your particle, which is kind of a nice idea, because if you have a cancer here, or if you had cancer here, you can tailor where that peak is and change it, and change your treatment so that you actually just irradiate the tumour rather than irradiating beyond the tumour, because wherever the particle is stopped, that's where the radiation exposure stops. And so the question is, that's a great form of radiation, so why is that not readily used? One of the limitations to using proton beam therapy, hadron therapy, ion beam oncology, these are all various terms for the same thing, is that the conventional accelerator technology you need to drive these energetic beams is very large and very expensive. And when you start to do a kind of cost-benefit analysis compared to X-ray therapy, which is very, very good, you start to think about whether it's worth installing one of these proton beam centres. But perhaps the accelerator technology could be smaller. It could be possibly cheaper, dare I say. Could it be driven by a laser plasma accelerator concept? That's one of the things that a lot of people in my field are looking at. And if we want to build one of those super gliders that will look at other things like dark energy, perhaps instead of having to rely on systems which are getting bigger and bigger with each generation of accelerator, we start incorporating a laser plasma accelerator as part of that staged process, so that we can actually move on. We can move on to a next generation of accelerator technology. And this is just one of the applications of accelerators outside fundamental physics. There are numbers of them in medicine, in imaging, and so on, using X-rays and gamma rays. And that's just one example I want to talk to you about. I'm moving on finally to my third example of laser plasma physics. And again, that's looking at another big thing about a question or challenge in society, moving on from cancer treatment and now on to electricity production. Electricity generation on the really grand scale. Now, I'm talking about electricity generation for the truly long term, for our generation and the generation after that, and the generation after that, and you could go on for ages. Because that really is a big challenge, because the way we generate electricity at the moment relies on Victorian engineering that requires a heat source. And most of our heat sources today come from burning fossil fuels, burning carbon and so on, or in some cases, nuclear reactions. But there's something else that we could do actually to generate electricity. And that's to take our inspiration from the way that the sun and every other star in our universe releases energy. Because it releases energy really well, really efficiently, and has done so for billions of years and will do for billions and billions and more. So how is nature releasing energy for its own good? Well, it's by a process called fusion, which again is a nuclear reaction, but it's slightly different to the fission that you will learn about in nuclear power stations. So fusion, as the name suggests, is fusing light atoms, light elements together. Now, these light atoms in this case are isotopes of hydrogen, so in the family of hydrogen. On the left we've got deuterium with 1 neutron, and on the right we have tritium, T, with 2 neutrons. And if you were able to get these 2 ions together and overcome their repulsion, the natural repulsion, if you could get them to come together and be bound by a strong nuclear force, and they form this new particle, helium, and they also spit out one of the neutrons as well. Now, the physicsy bit about this is actually when you start to look at the masses of those isotopes that you start with, compare it to the mass of the helium and neutron coming off. Because what you'll find is that the mass on this left-hand side is actually more than the mass on this right-hand side. Now that, I hope, is triggering some kind of uncomfortableness there, but where has that mass gone? Because mass is a form of energy. And like any other energy, it can't be created, it can't be destroyed. It's constantly evolving from one form or another. And some might say that that's kind of the basis of life itself, is energy constantly transforming from one form to the other. And that is very elegantly expressed in this beautiful equation, the main equation that I have in this talk, by E equals mc squared. As simply as that. Saying that that mass hasn't disappeared. It has simply been converted into a different form of energy by multiplying it by a huge number, c squared. So despite that mass change being tiny for each fusion reaction, the energy release is quite vast. And the energy release is huge compared to chemical release by burning stuff, kind of back to the old ages there. And the potential that these fusion reactions have as a way of releasing energy is quite impressive. Because deuterium, the Ds, are sometimes called heavy water. They're actually extracted, you can be extracted from seawater itself. So if you were to collect a beaker full of seawater, extract all the Ds, or the deuteriums, fuse them with tritiums, you would release an energy equivalent of a tanker full of fuel, which is quite impressive. Now, what would you do with that energy? Well, you'd use an energetic neutron, which has absorbed most of the energy. It's absorbed most of the energy in a kinetic form, in a movement force. It's flying out of your target chamber, out towards the walls. It hits the sides of your target chamber and is absorbed. That kinetic energy is transferred into heat energy. That heat energy is used to boil water to produce steam, which then turns turbines and generates electricity. So it's quite ironic, actually, they're developing this extremely exotic form of heat energy to drive what is technically Victorian engineering. But that's how we work at the moment, and we have power stations all over the world serving civilizations in every country. So actually all we need to do is keep that energy source going for a long time. And using an energy source that is clean, you do notice there's no carbon involved there, which is a really good thing for our future and our climate. Talking about extracting fuel from water, from seawater, well, there's plenty of that. We've got to work on getting enough tritium, but there's no problem there, because actually there's a clever way of producing tritium in your target chamber by using some of those neutrons to bombard into lithium, and through a nuclear reaction they'll produce tritium. So that's not bad. There's a fair amount of lithium around, so I think we'll be okay there. It's inherently safe. So those energetic neutrons bombarding into the chambers won't just produce a bit of heat energy, they'll also make the kind of chamber walls a bit radioactive as well. It's certainly not the kind of radioactive waste that we produce by standard nuclear techniques. It's the kind of radioactive waste that you might want to bury for around 100, 150 years, which I know sounds a bit much, but the stuff we're producing at the moment, you have to bury in deep holes for thousands of years. And that's something that, in my world, is a bit responsible for future generations. So 100, 150 years, shadow grave, it's sometimes called, not a bad alternative. Now the big question here, for us physicists and engineers, is to figure out, can we do this on Earth? Can we copycat what the sun is doing and make these fusion reactions happen again and again and again? Well, if you know by now, the answer is yes, yes we can. With big, powerful lasers. Because I've already mentioned this as well, haven't I, to say that the lasers can produce the conditions at the centre of the sun. So you're just irradiating a tiny pellet, maybe a few millimetres in diameter, with loads of lasers. You're superheating the surface and super compressing at the same time. You can squeeze those Ds and those Ts down to densities that are on the order of 20 times that of lead. And if you're really clever, you'll superheat this to about 50 million degrees Celsius. Really high temperature, really high density. And that's when you'll ignite loads of fusion reactions. That's the perfect condition for fusion reactions to take place. If we can do that on Earth, and if we can do that at 10 times a second, we have a really, really good design for a fusion-powered, fusion-generated power station. Now, how are we doing experimentally? How are we doing that as a world service at the moment? This is a picture of the National Ignition Facility in the US. It's in California. They have built 192 laser beams. This is just half of them now, half of the bay. And they are all focused into a target chamber that is about 10 meters in diameter. It's quite a colossal feat of engineering right there. A colossal installation to focus a load of lasers onto a tiny pellet that is literally, a couple of millimeters in diameter. But what they're doing there is using those 192 laser beams to superheat and supercompress deuterium and tritium ions to achieve fusion reactions. But not only just to do fusion, because we've done fusion reactions before, we've actually done them for many, many years. The key thing here is, can we release more energy in this process than we actually have to put into the lasers themselves to get the process going? Because as you can imagine, there's quite a large amount of electrical power that goes into firing these lasers every time you press the button. But if we can generate more, or release more energy in this process than we do to make the process happen, then you have a really great design for a power station. And again, anyone who's been keeping up to date in the last week, we're not doing too badly actually with lasers. The National Ignition Facility released a paper into Nature publishing recently to say that the amount of energy that's absorbed by the fuel, so we have to be very careful here, it's not the amount of energy that went into the lasers themselves, but the amount of energy that went into the fuel, because some of it was reflected, remember, from a solid surface. More energy was released by all the fusion reactions happening that actually was absorbed by the fuel. So you have almost a net gain of energy there, which is really interesting. There was lots of coverage of that actually, which is really nice. And even in the Financial Times as well, with lasers blast away forward. Lasers are great for puns in journalism. But this is what we're all ultimately planning to head for. Because once we've got to the point where we're getting more energy out than we even put into the lasers themselves, you really do have a healthy design for a power station that would look, I guess, a little bit like this. So not that far off from what we're used to now, so it's not too bad to build those around. And you'd have all your lasers firing onto this target chamber here, releasing those energetic neutrons, which give you a kind of bath of heat energy. And again, this is something which is very familiar, just using turbines that are producing electricity that goes off into the national grid. The key question here is, can we make this process happen? And then, once we've done the physics to show that we can do it and we can understand the process, it then becomes a job of engineering, materials, robotics, and all these kind of things that have to come together to see these things come to life, to see this research become reality. So that kind of draws me into a close now after my 3 examples of what we do with extreme laser intensity. It's not just for creating these beautiful pictures, it's actually to explore an area of physics, plasma physics, that is not only extraordinary in kind of explaining the world that we live in, but is also giving rise to incredibly powerful and high impact technology. So now it's up to you again with your voting pads. So what would you do? with the most powerful laser in the world, if you had some experimental beam time on the lasers that I work with, would you, one, use them to understand the most extreme states of matter and astrophysics? Two, would you look at plasma accelerators? Or three, laser fusion for energy? Okay. Whoa. That's quite a majority looking at laser fusion for energy right there. And that's quite an interesting ratio actually there I'm seeing between 1 and 2. Because 1, which is the Lab Astro, the laser plasma extreme physics thing, that's kind of like the relatively new kid on the block. It's kind of new fashion at the moment in plasma physics, because it's only recently that the lasers have been good enough to generate these extreme conditions that we can actually start doing experiments and probing them in the lab. But I guess this is representative of how quickly that field will grow in the next few years. And 2, looking at plasma accelerators, only 8%. That's what actually I do. I look at plasma accelerators. The cancer therapy thing was what got me into my PhD, and I'm now looking at laser-driven beams of X-rays to freeze frame engineering components that can rotate at very, very high speeds. And then 79% of you, overwhelmingly, want to use these lasers for the good, to save the world from its energy crisis in the form of laser fusion. And that is quite a nice point to end on there, because that is also the thing that got me into plasma physics in the very, very beginning. Actually, that's what, right when I was just finishing my first degree, I learned about laser fusion. I thought, oh my God, that's the point of physics, is to save the world through electricity generation. And it still is a really, really big part of plasma physics. The plasma physics community is quite small in comparison to other areas of physics, like particle physics, for example. But the majority of the plasma physicists started or are still studying fusion energy, so massive effort. So finally, just to wrap up, I've kind of taken you on a little journey through what you can do with really powerful lasers, and we've looked at some extreme conditions, some that are really not found here on this earth. And through that, you make extreme measurements. So you're measuring things that happen extremely quickly, at extremely high temperatures, at extremely high densities. And that leads, in some cases, to extremely high applications. Whether those applications are simply learning about the world that we live in, where do we come from, what are these extreme astrophenomena that happen in the early universe, how all those things happen, and what are the other extreme states that we live in? Looking at the fundamentals of matter itself. But the extreme physics, the foundation that lays, not only leads to a better understanding about the universe that we live in, but it also means that we can design tomorrow's technology today, in the form of laser fusion, or perhaps in the form of plasma accelerators. That's, to me, that is what my perspective of physics is. It's a foundation in knowledge that allows us to understand the world and perhaps even improve it. Thank you for listening.